Space is the ultimate mystery, a vast, uncharted frontier filled with wonders that defy our understanding even today. Think we've got it all figured out. Think again. Out there, beyond the glow of familiar stars, lie enigmas so strange, so baffling, that even the brightest scientists are left scratching their heads. From eerie signals echoing across the cosmos to celestial objects behaving in ways that shouldn't be possible, the universe is packed with phenomena that challenge everything we think we know. And here's the wildest part: these aren't just minor curiosities. They're cosmic riddles that could rewrite the rules of physics, alter our understanding of reality, or even hint at forces beyond our wildest imagination. What if I told you there's a place in space where time seems to stand still, or that entire galaxies are vanishing without a trace, leaving behind nothing but questions? These aren't plot twists from a sci-fi movie. They're real, documented mysteries that astronomers are grappling with right now, and that's just the tip of the cosmic iceberg. Over the next few minutes, we'll dive into 25 of the most mind-bending, spine-tingling phenomena in the universe, phenomena so bizarre they make black holes look ordinary by comparison. We're talking about stars that flicker like faulty light bulbs, planets that shouldn't exist, and cosmic structures so enormous they defy the very laws of the universe. This isn't just a journey through space, it's a journey to the edges of human knowledge. Every discovery we make only seems to reveal how much we still don't understand. But that's the thrill of it, isn't it? The universe isn't just a cold, empty void. It's alive with mystery, whispering secrets we're only beginning to hear. So buckle up, because we're about to explore the unexplainable, the unbelievable, and the downright eerie. By the end, you might just look up at the night sky and wonder, what else is out there waiting to be discovered? One of the most spine-tingling cosmic mysteries began on an ordinary August evening in 1977, when a radio telescope in Ohio picked up something impossible to ignore. The Big Ear Telescope at Ohio State University, a massive ear trained on the heavens, caught a blistering burst of radio waves so powerful, so unusual, that the astronomer who discovered it scrawled, "Wow," in red ink right on the data printout, and just like that, the wow signal was born. For 72 electrifying seconds, this signal blasted through the void, strong enough to stand out against the usual cosmic static, then vanished without a trace. Imagine tuning an old radio between stations and suddenly hearing a voice shout your name, only for it to disappear the moment you lean in closer. That's how jarring, how haunting this moment was for scientists. Decades later, we still have no idea where it came from. The signal was narrowband, meaning it was focused on a specific frequency, the kind we'd expect from an artificial source, not a random cosmic event. It matched predictions for how an intelligent civilization might broadcast its presence across the stars. And here's the kicker: it originated from a seemingly empty patch of space near the constellation Sagittarius, with no known stars or planets to explain it. Skeptics have thrown out theories. Maybe it was a comet's hydrogen cloud or a bizarre stellar flare, but none fit perfectly. The signal's structure was too clean, too deliberate. And despite countless efforts to catch it again, the universe has stayed stubbornly silent. No repeats, no echoes, just that one cryptic 72-second scream into the void. Could it have been aliens, a malfunction, or something we haven't even dreamed up yet? The wow signal taunts us with possibilities, a cosmic riddle that refuses to be solved. It's a reminder that sometimes the universe sends us a message, not to give us answers, but to remind us how much we still have left to learn. Now picture this: you're looking up at the night sky, tracing constellations with your finger, but here's the unsettling truth: what you're seeing is barely a fraction of what's actually out there. In fact, the stars, planets, and galaxies we can observe make up less than 5% of the universe. The rest, a ghostly, invisible presence known as dark matter. It doesn't emit light, it doesn't reflect it, and yet its gravitational grip is so powerful it bends the very fabric of space itself. How do we know it's there if we can't see it? Think of it like wind. You can't see the air moving, but you can watch tree branches sway under its force. In the same way, dark matter's gravity tugs at everything around it. Galaxies rotate faster than they should, as if held together by unseen hands. Light from distant stars warps around invisible masses like water flowing around a rock. Even the way galaxies cluster together points to something massive lurking in the shadows. Scientists have spent decades chasing this cosmic phantom. One leading theory suggests dark matter could be made of weakly interacting massive particles. These hypothetical particles would be heavy, slow-moving, and barely interact with normal matter, slipping through our detectors like smoke through a sieve. Another idea points to action's ultralight particles so tiny, they behave more like waves than solid objects. Then there's the possibility we've got gravity all wrong, and maybe dark matter isn't a thing at all, but a flaw in our understanding of the universe's fundamental rules. The hunt has led to extraordinary experiments. Deep underground, in abandoned mines and beneath mountains, detectors wait for the faintest whisper of a dark matter collision. In space, telescopes map the distortions in starlight, tracing the invisible scars left by this enigmatic substance. And yet, after all this time, dark matter remains elusive, a cosmic game of hide and seek where we're still fumbling in the dark. What's fascinating isn't just the mystery of what dark matter is, but what its existence tells us about the universe. It's a humbling reminder that everything we know, everything we are, is just a speck in a vast, unseen ocean. The cosmos is playing by rules we haven't fully uncovered, and dark matter, it's the universe's way of whispering you're missing something. If dark matter is the universe's hidden scaffolding, dark energy is its shadowy puppet master, a force so baffling it's literally tearing reality apart at the seams. Here's the kicker: while dark matter pulls galaxies together with its gravity, dark energy does the exact opposite, pushing the cosmos outward at an ever-increasing speed. And the wildest part, we have no idea what it actually is. This cosmic plot twist began in the late 1990s, when astronomers made a discovery that upended everything we thought we knew about the universe's fate. By studying distant supernovas, exploding stars that act as cosmic mile markers, they noticed something chilling. These stellar explosions weren't just far away, they were dimmer than expected, meaning the space between them and us had stretched more than physics predicted. The universe wasn't just expanding, it was accelerating, as if some invisible hand had pressed down on the gas pedal of reality itself. That's dark energy in action. Unlike gravity, which weakens with distance, dark energy seems to grow more dominant as the universe expands, its repulsive force unchained by the emptiness it creates. Imagine blowing up a balloon with tiny dots on its surface. As the balloon inflates, the dots move apart, but now picture the balloon inflating faster and faster on its own, with no one blowing into it. That's the eerie effect dark energy has on the cosmos. The numbers are staggering. Dark energy makes up roughly 68% of the universe's total energy, dwarfing even dark matter. But its nature, a complete enigma. Some theorists suggest it's a property of space itself, what Einstein once called the cosmological constant, a kind of background energy woven into the vacuum of reality. Others propose it's a dynamic field, like an invisible fluid filling the universe, its strength shifting over time. Then there's the radical idea that our understanding of gravity is fundamentally flawed, and dark energy isn't a thing at all, but a sign that Einstein's equations break down on cosmic scales. What keeps scientists up at night isn't just the mystery, it's the implications. If dark energy continues unchecked, it could lead to a big rip, where galaxy clusters, stars, even atoms are torn apart in a violent cosmic finale. Or it might fade away, allowing gravity to reclaim dominance. Or most unsettling of all, it could be just the first clue to forces we haven't even imagined yet, rewriting the story of the universe in ways we can't foresee. Every telescope, every supernova observation, every deep space probe is hunting for answers, but dark energy remains the ultimate cosmic wild card. It's the universe's way of reminding us, just when you think you've got the rules figured out, space throws you a curveball that changes everything. Imagine a pulse of energy so intense it outshines entire galaxies, but only for the blink of an eye. That's the enigma of fast radio bursts, or FRB, cosmic lightning strikes that flash across the universe in just milliseconds, packing more energy than our sun emits in days. First detected in 2007, these bursts arrive without warning, vanishing almost before astronomers can point their telescopes. And the strangest part, we still don't know what's firing them into the void. These bursts aren't just rare, they're elusive. Most happen once and never repeat, like a firecracker popping in the dark. But a handful have been caught flashing multiple times, teasing scientists with cryptic patterns. In 2020, one FRB from a galaxy 3 billion light-years away pulsed like clockwork every 16 days for over a year, a cadence that ruled out random cosmic collisions. Another traced back to a highly magnetized neutron star called a magnetar, where twisted magnetic fields could snap like rubber bands, unleashing these blistering radio waves. Could magnetars be the key? These collapsed stellar cores have magnetic fields 1 trillion times stronger than Earth's, capable of shredding atoms into glowing plasma. When their crusts crack under pressure, they might unleash tsunamis of particles that ignite FRBs. But some bursts defy even this explanation, arriving with energies too extreme for known physics. That's led to wilder theories: cosmic strings vibrating from the birth of the universe, black holes evaporating into bursts of radiation, or even, yes, it's been suggested, alien megastructures beaming signals across interstellar space. Catching these bursts is like cosmic detective work. Telescopes like CHIME in Canada scan the sky constantly, waiting for that split-second flicker. When one hits, observatories worldwide scramble to triangulate its origin, racing against the clock before it fades. Yet for every burst we catch, thousands likely slip by unnoticed, their secrets lost in the noise of the cosmos. The more we learn, the deeper the mystery grows. FRBs aren't just oddball phenomena, they're probes into the universe's most extreme environments, testing the limits of physics itself. Each burst is a message in a bottle, hurled from distances we can barely fathom. And until we crack their code, they'll keep reminding us the cosmos is far stranger, far more inventive than we ever dreamed. Right now, as you read this, our galaxy, along with hundreds of thousands of others, is being pulled towards something unseen with unimaginable force. Picture floating in a river, unable to swim against the current, dragged relentlessly toward a waterfall you can't yet see. That's the Great Attractor, a gravitational nightmare lurking in the shadows of space, tugging at everything around it with the subtlety of a cosmic whirlpool. Here's the kicker: we can't even look directly at it. The Great Attractor hides behind the so-called zone of avoidance, a region of the sky obscured by the thick dust and stars of our own Milky Way's galactic plane. It's like trying to peer through a dense fog while standing in the middle of a blinding spotlight. But thanks to infrared and radio telescopes piercing through that cosmic curtain, we've glimpsed enough to know something colossal is there, something with the mass of tens of thousands of Milky Ways. So what's yanking us toward it? The leading suspect is the Norma Cluster, a dense gathering of galaxies about 250 million light-years away. But here's the twist: even its combined gravity doesn't fully explain the sheer force we're observing. Some researchers suggest the Great Attractor might be part of something even larger, a mind-bending structure called the Laniakea supercluster, a filamentary web of galaxies spanning 500 million light-years with the attractor as its gravitational center. Think of it as a cosmic grand central station with galaxies like commuters funneling toward its unseen platforms. Then there's the darker possibility. What if the Great Attractor isn't just a cluster, but a previously unknown type of mass, or worse, a sign that our understanding of gravity itself is incomplete? Alternative theories propose exotic phenomena like primordial black holes from the early universe, or even defects in the fabric of space-time left over from the Big Bang. The scariest part, this isn't just academic curiosity. The Great Attractor's pull is shaping the destiny of our local cosmic neighborhood, herding galaxies into a future collision course we can't escape. It's a reminder that even in the vastness of space, we're not floating freely. We're caught in an invisible current, swept toward a mystery we're only beginning to map. Every new observation peels back another layer, revealing just how much of the universe remains hidden in plain sight. Out in the constellation Cygnus, roughly 1,400 light-years from Earth, a star behaves unlike any other we've ever seen. Meet KIC 8462852, better known as Tabby Star, named after astronomer Tabitha Boyajian, who first brought its bizarre antics to the world's attention. At first glance, it looks ordinary, a yellow-white star not too different from our own sun. But its light tells a different story, flickering and fading in ways that defy every known cosmic rulebook. The strangeness began when NASA Kepler Space Telescope, designed to hunt for exoplanets by spotting regular dips in starlight, caught something utterly unexpected. Planets typically dim a star's light by a predictable 1 or 2%, like clockwork, as they orbit. Tabby's Star, it plunges by 22% at times, cataclysmic drops that last for days or even weeks with no rhythmic pattern. Imagine a lamp in your house suddenly dimming to half its brightness for no reason, then flicking back on days later. Now picture that lamp being a star 1,000,000 times larger than Earth. That's the level of cosmic weirdness we're dealing with. Theories exploded faster than a supernova. One early, tantalizing idea suggested an alien megastructure, like a Dyson swarm of solar collectors, might be blocking the star's light. After all, what else could explain such massive, irregular shadows? But before we jump to extraterrestrial conclusions, scientists scrambled for natural explanations. Maybe a family of giant comets, hundreds of thousands of them, were vaporizing as they spiraled into the star, creating thick clouds of debris. Or perhaps the star had recently devoured a planet, leaving behind a chaotic ring of dust and rubble. Some even proposed an undiscovered companion star, warped by gravity into a bizarre, light-blocking dance. Yet every hypothesis hits a snag. Comets couldn't explain the sheer scale of dimming. A planetary collision would have left infrared traces we don't see, and no companion star has been spotted, no matter how hard we look. Even stranger, historical data reveals Tabby Star has been gradually dimming over the past century, dropping its brightness by a staggering 14% overall, something stars of its type simply don't do without obvious cause. Recent observations only deepen the puzzle. In 2017, the star's light plummeted again, and telescopes worldwide trained their lenses on it like detectives staking out a suspect. What they caught was equally baffling. The light dimmed more at some wavelengths than others, as if whatever was blocking it wasn't solid but patchy, like a cloud of fine dust. Yet even that doesn't fully fit. Dust should scatter light uniformly, not in these jagged, unpredictable patterns. Tabby Star is more than a cosmic oddity. It's a mirror held up to our own ignorance. For every natural explanation we test, the star seems to laugh, throwing another curveball. It's forced astronomers to question assumptions, to wonder if we're missing some fundamental piece of stellar behavior. Maybe it's a rare phase in a star's life, something we've just never witnessed before. Or maybe, just maybe, it's something no one has ever imagined. Right now, telescopes keep watch, waiting for the next mysterious dimming, the next clue. And every flicker, every unexplained fade is a reminder. The universe doesn't owe us easy answers. Sometimes it gives us a star that winks at us from the void, daring us to figure it out. In the vast emptiness between planets where gravity's grip should be predictable and precise, two spacecraft defied every calculation. Pioneer 10 and 11, launched in the early 1970s to explore Jupiter and Saturn, became famous for another reason entirely: their baffling, unplanned slowdown. As they hurtled toward the outer solar system, scientists noticed something strange. Both probes were losing speed faster than Newton's laws predicted, as if an invisible hand were gently pressing the brakes. This discrepancy, dubbed the Pioneer Anomaly, sparked a decades-long cosmic whodunit that pitted textbook physics against the tantalizing possibility of uncharted forces. At first, the numbers seemed trivial: a deceleration weaker than a mosquito's push, barely noticeable over short distances. But across billions of miles, that tiny drag added up, pulling the Pioneers off course by thousands of miles. The effect was consistent, unrelenting, and identical between both spacecraft, ruling out random malfunctions. The implications were staggering. If this wasn't human error or instrument glitches, it hinted at physics beyond Einstein, a flaw in our understanding of gravity itself. Theories erupted like solar flares. Maybe dark matter was clustering near the sun, tugging at the probes. Or perhaps general relativity needed tweaking at solar system scales, requiring new equations to explain the anomaly. Some even proposed exotic ideas like modified inertia or quantum gravity effects, but the most plausible culprit, something far more mundane: heat. Pioneer's nuclear power sources glowed at over 200 degrees Celsius, radiating warmth unevenly from their angled sides. Like a tea kettle venting steam, this heat could have pushed back on the probes, creating the illusion of extra deceleration. In 2012, painstaking analysis of recovered telemetry data and thermal models seemed to confirm this. Once engineers accounted for every watt of heat radiating from the spacecraft's bodies, most of the anomaly vanished. Case closed, not quite. Even after the thermal explanation, a whisper of the anomaly remained, a residual effect too small to dismiss entirely. Was it unmodeled heat, some quirk in the spacecraft's design we still don't understand? Or could it be evidence of something deeper, a ghost in the machinery of gravity waiting to reveal itself? Future missions like NASA New Horizons now carry instruments designed to spot similar effects, hunting for answers in the icy dark beyond Pluto. The Pioneer Anomaly is a masterclass in scientific humility, a reminder that even in the familiar confines of our solar system, the universe keeps secrets. It's not just about solving a mystery, it's about asking whether we've been missing something fundamental all along. Every unexplained fraction of acceleration, every tiny deviation in a probe's path, whispers the same question: what if we've only scratched the surface? The universe is staggeringly vast, with hundreds of billions of galaxies, each hosting billions of stars, many of them orbited by planets in habitable zones. Given those numbers, the odds seem overwhelming that life, even intelligent life, should be common. And yet, when we listen, when we search, the cosmos answers with silence. This glaring contradiction is the Fermi Paradox, the unsettling gap between what statistics say should be out there and the eerie emptiness we actually observe. The paradox gets its name from physicist Enrico Fermi, who, during a casual lunchtime conversation in 1950, famously asked, "Where is everybody?" If civilizations arise even slightly more advanced than ours, they should have had millions or billions of years to spread across the galaxy. So why haven't we found a single artifact, signal, or whisper of their existence? One chilling possibility is the Great Filter, a theoretical barrier that prevents life from advancing to interstellar scales. Maybe the filter lies in our past. The leap from simple chemistry to self-replicating life is so astronomically unlikely that Earth is a freak accident. Or worse, the filter could still be ahead of us, an inevitable catastrophe like nuclear war, runaway AI, or an unforeseen cosmic disaster that snuffs out civilizations before they can spread. If that's true, humanity's silence might be a grim warning. Every civilization hits a wall, and none survive long enough to become visible. But not all explanations are so bleak. The zoo hypothesis suggests advanced civilizations do exist. They're just deliberately avoiding us, treating Earth like a nature preserve or a cosmic lab. Imagine ants in a forest unaware of the scientists observing them from a distance. Alternatively, we might be searching the wrong way. Alien communication could use neutrino beams, quantum entanglement, or other technologies we haven't even imagined, rendering their signals invisible to our primitive telescopes. Then there's the rare Earth theory. Perhaps complex life requires such a precise cocktail of conditions: a stable star, a protective moon, plate tectonics, even the right kind of galaxy, that habitable worlds are vanishingly scarce. Or maybe civilizations self-destruct not through catastrophe, but by abandoning physical expansion entirely, opting instead to upload their minds into virtual realities, leaving the outer universe barren of visible activity. The scariest thought: we might be alone, not just in our galaxy, but in the entire observable universe, a fluke of chance in an otherwise lifeless expanse. Or perhaps the truth is something no one has dared to theorize yet. Every potential answer to the Fermi Paradox forces us to confront uncomfortable truths about our place in the cosmos, the fragility of intelligence, and the unnerving possibility that the universe doesn't want to be noticed. Until we find proof, or until someone or something finds us, the silence remains, and the question lingers, echoing across the stars: are we really all there is? The moon hangs in our night sky as a silent, cratered companion, but billions of years ago, it may have pulsed with a magnetic field rivaling Earth's. Today, lunar rocks tell a cryptic tale. Trapped within their ancient crystals are traces of magnetization, evidence that our airless, geologically quiet neighbor once crackled with unseen energy. How could something so small and seemingly inert have generated such a force? And why did it vanish? The answers could rewrite not just the moon's history, but our understanding of how rocky worlds evolve across the cosmos. The mystery starts with dynamo theory, the same process that powers Earth's magnetic field today. On our planet, swirling molten iron in the outer core acts like a colossal electric generator, creating a protective magnetic shield. But the moon's core is far smaller and cooler, with no active plate tectonics to stir its depths. So what kicked its dynamo to life? One leading theory points to sheer cosmic violence. In the moon's youth, Earth's gravity may have stretched and squeezed its interior like putty, generating enough friction to heat the core and jumpstart a magnetic field. Alternatively, a massive asteroid impacts common in the early solar system could have rocked the moon's core, churning its molten metal with each collision like a spoon stirring soup. Then there's the crystallization theory. As the moon's molten core cooled, buoyant minerals might have risen while heavier iron sank, creating convective currents strong enough to spin a dynamo. But here's the catch: this process would have required the moon to lose heat slowly, which contradicts evidence of its rapid cooling. Unless, and this is where it gets intriguing, radioactive elements like potassium and thorium littered the core, acting as natural nuclear reactors that prolonged its molten state. Lunar samples do show traces of these elements, but not enough to fully explain the field's longevity. The real stumper isn't how the field started, though, it's how it died. Around 1 billion years ago, the moon's magnetism sputtered out, leaving its surface exposed to solar winds and cosmic radiation. Some researchers argue the core simply froze solid, like a battery drained of power. Others propose a catastrophic impact disrupted the dynamo permanently, like a hammer smashing a watch's gears. But the most haunting possibility: the moon's field didn't vanish, it's still there, just locked away. Weak magnetic patches scattered across the surface, called lunar swirls, hint at fossilized remnants of the old field, preserved like shadows in the dust. This isn't just academic curiosity. Unraveling the moon's magnetic past could reveal why some worlds become habitable while others stagnate. Earth's field shields life from deadly radiation. Had ours faded, evolution might have taken a radically different path. And if tiny, rocky moons once common in the cosmos could generate their own shields, it raises the odds that life found footholds in places we'd never think to look. Every rock brought back by Apollo, every magnetic whisper detected by orbiters, chips away at the mystery, but the moon isn't giving up its secrets easily. It's a celestial puzzle box daring us to crack it open. Black holes aren't just cosmic vacuum cleaners, they're shredders of reality itself, tearing apart the very fabric of information. And that simple fact has sparked one of the most heated debates in modern physics, the black hole information paradox. At its core, this isn't just a scientific quarrel, it's a clash of titans, pitting Einstein's theory of general relativity against the strange rules of quantum mechanics. The question is deceptively simple. When something falls into a black hole, is its information lost forever? The answer could rewrite our understanding of the universe. According to general relativity, black holes are the ultimate one-way streets. Their gravitational pull is so fierce that not even light can escape past the event horizon, the point of no return. Anything crossing that boundary is crushed into oblivion at the singularity, a place where space and time cease to have meaning. If that's true, then all the information about what fell in, whether it's a star, a spaceship, or an unfortunate astronaut, vanishes from the universe permanently. But here's the problem. Quantum mechanics insists that information can never be destroyed. It might get scrambled, hidden, or transformed, but it must persist in some form. These two pillars of physics, both rigorously tested, give us completely opposite answers. So who's wrong? Enter Stephen Hawking. In the 1970s, he made a startling prediction. Black holes aren't completely black. They leak through a bizarre quantum effect near the event horizon. Pairs of virtual particles can pop into existence, one falling in, the other escaping as radiation. Over eons, this Hawking radiation causes black holes to evaporate, leaving behind nothing. No trace, no information, just empty space. That was the bombshell. If Hawking was right, information truly was being erased, violating quantum theory. The physics community split into warring camps. Some, like Hawking himself, argued information was lost. Others, like Leonard Susskind, insisted it had to be preserved even if we didn't know how. The breakthrough came from an unexpected direction: holograms. In the 1990s, physicists proposed that all the information swallowed by a black hole might be encoded on its surface, the event horizon, like a cosmic hard drive storing data in 2 dimensions instead of 3. This holographic principle suggests that what we perceive as a 3-dimensional loss is actually a transformation, with information imprinted on the horizon in Planck-scale pixels before being radiated back out, scrambled but intact. Imagine burning a book. Its pages turn to ash, but if you had perfect knowledge of every molecule's position, you could theoretically reconstruct it. Black holes might do something similar, just on a quantum scale. Recent experiments have added fuel to the fire. In 2016, gravitational wave detectors observed black holes merging, and the resulting signals hinted at information preservation. Even more compelling, theoretical work on soft hair, subtle imprints left on a black hole's horizon, suggests information isn't lost but subtly altered. The debate is far from settled, though. Some researchers argue holography kicks the can down the road without fully solving the paradox, while others propose radical ideas like black holes leading to other universes where the information reappears. What's at stake isn't just a technicality, it's the foundation of physics itself. If information can vanish, our understanding of cause and effect, of time, even of reality's reliability, crumbles. But if it's preserved, hidden in some quantum code we haven't cracked yet, we might be on the verge of a theory that unites gravity and quantum mechanics at last. Every black hole out there is more than a cosmic mystery. It's a laboratory testing the limits of human knowledge, and the universe, it's waiting to see if we're smart enough to figure it out. In October 2017, astronomers spotted something streaking through our solar system that instantly rewrote the rules, an object unlike anything we'd ever seen before. Named Oumuamua, Hawaiian for scout, this interstellar visitor wasn't just passing through, it was accelerating, defying gravity's pull with no visible explanation. At first, scientists assumed it was a comet, an icy wanderer from another star system, but Oumuamua refused to fit the mold. No tail of gas or dust, no coma glowing around it, just a bizarre, elongated shape, tumbling end over end like a cosmic pancake flung through space. Then came the real shocker, its speed. Comets typically get a boost from outgassing sunlight vaporizing their ice, creating jets that act like natural thrusters. But Oumuamua showed no signs of this, no visible debris, no spectral hints of water or carbon dioxide boiling off. Yet somehow it was picking up speed as it raced away from the sun, as if propelled by an unseen force. That's when the theories went wild. Maybe it was a hydrogen iceberg vaporizing invisibly in sunlight, or a fractal-like dust bunny of ultra-light material, porous enough to catch solar radiation like a sail. Or as one Harvard astrophysicist controversially suggested, a relic of alien technology, an abandoned probe or solar sail from a distant civilization. The debate raged because Oumuamua didn't just challenge our categories, it obliterated them. Too fast for a typical asteroid, too inert for a comet, too oddly shaped for anything natural we'd catalogued before. Its reddish hue suggested it had been bombarded by cosmic rays for millions, maybe billions, of years, a traveler from a star system we may never identify. And then, just as suddenly as it appeared, it vanished beyond our telescope's reach, leaving behind more questions than answers. What makes Oumuamua unforgettable isn't just its mystery, but what it represents, proof that our cosmic neighborhood gets visitors we don't understand. It's a reminder that the universe is stranger, more inventive than our textbooks allow. Every new interstellar object we spot, every flicker of motion from the depths, could be another Oumuamua, another chance to ask, what else is out there slipping past us unnoticed? When we peer into the depths of the universe, we expect chaos, randomness on the grandest scale. But in 2005, astronomers stumbled upon something that sent chills down the spines of cosmologists, an eerie, statistically impossible alignment in the oldest light we can observe. Dubbed the axis of evil, this cosmic curveball refers to a bizarre pattern in the cosmic microwave background, the afterglow of the Big Bang, where temperature fluctuations seem to line up suspiciously with the plane of our solar system. It's as if the universe left a fingerprint and it's pointing right at us. Here's why this is so unsettling. The cosmic microwave background, or CMB, should be isotropic, uniform in all directions, like the surface of a perfectly smooth balloon. After all, the Big Bang blasted matter and energy outward in every direction, and over 13.8 billion years, that randomness should have settled into a cosmic sea of equal chance. But when scientists mapped the CMB's tiny temperature variations, fluctuations as subtle as 1 part in 100,000, they found an unexpected pattern. The hotter and colder spots weren't scattered randomly. They seem to cluster along an invisible axis that weirdly aligns with our ecliptic, the plane in which Earth and the planets orbit the Sun. The implications are staggering. Either this is the most improbable coincidence in the history of science, or something fundamental in our understanding of the universe is wrong. One possibility, our solar system might somehow be cosmically special, a thought that flies in the face of the Copernican principle, the bedrock idea that Earth doesn't occupy a privileged place in the cosmos. Alternatively, the CMB's alignment might hint at a preferred direction woven into the fabric of spacetime itself, like invisible cosmic scaffolding left over from the universe's birth. Skeptics argue it could be an artifact, a trick of our perspective, contamination from the Milky Way's dust, or even an unaccounted-for quirk in how we process the data. But the more we refine our measurements, from Planck satellite data to ground-based observatories, the more stubborn the signal becomes. Some theorists have ventured into wilder territory, suggesting pre-Big Bang physics, multiverses leaking into our reality, or even undiscovered forces that shaped the early universe like a potter spinning clay. What's undeniable is this: the axis of evil exposes how much we still don't know. The CMB is supposed to be the ultimate snapshot of a young, chaotic universe, yet here it is, whispering of hidden order. Whether it's a flaw in our models or a clue to deeper truths, one thing's clear: the universe still has surprises up its sleeve. And until we crack this cosmic code, it's a reminder that even the oldest light in the sky can still hold dark secrets. In the vast cosmic web where galaxies cluster like glittering cities, there exists a desert so vast, so unnaturally empty, it defies everything we know about the universe's structure. This is the Boötes Void, a spherical chasm in space stretching 330 million light-years across, containing barely 60 galaxies where there should be thousands. To put that in perspective, if the Milky Way were a single grain of sand, the Boötes Void would be an empty football stadium with just a few grains scattered in one corner. It's not just a gap, it's a cosmic anomaly, a hole punched through the fabric of reality with no clear explanation. How does something this empty even form? The leading theory points to the universe's frothy infancy. After the Big Bang, matter wasn't distributed evenly. It clumped into dense regions separated by bubbles of near-nothingness. Over billions of years, gravity amplified these differences, pulling galaxies into filaments and leaving behind voids like Boötes. But here's the catch: this void is too empty, too large. Simulations suggest it shouldn't exist in its current form. Some researchers propose it's the result of multiple smaller voids merging, like soap bubbles combining into one giant cavity. Others wonder if an unknown force, a relic from the universe's first seconds, pushed matter away from this region, leaving behind a scar in space-time. Then there's the darker, more speculative idea. What if the Boötes Void isn't natural at all? Advanced civilizations, if they exist, might harness energy on scales we can't fathom. Theoretically, a Kardashev Type 3 civilization, one capable of utilizing the energy of entire galaxies, could deliberately clear a region of space, leaving behind a void as a byproduct of their unfathomable engineering. Or perhaps it's a cosmic fossil, the aftermath of a cataclysmic event where galaxies were somehow erased, not by destruction, but by something even stranger, like a collision with a parallel universe or a localized vacuum decay event rewriting the laws of physics. The irony of the Boötes Void is that its emptiness makes it impossibly interesting. Every galaxy within it becomes a scientific treasure, a survivor in a realm where galaxies shouldn't exist at all. Studying them might reveal clues. Are they older, younger, or different in composition from their neighbors? Do they show signs of unusual activity, as if whatever cleared the void spared them for a reason? Even the void's edges are peculiar, with some galaxies appearing stretched, as if clinging to the precipice of this cosmic abyss. What terrifies astronomers isn't just the void's existence, it's what it implies. If structures this large can form naturally, our models of cosmic evolution might be missing a crucial piece. But if they can't, then the Boötes Void stands as a billboard for the unknown, a silent challenge to our understanding of the universe. It's a reminder that space isn't just full of wonders sometimes, the wonder is in what isn't there. And until we solve this riddle, the void will keep staring back at us, dark and depthless, daring us to explain it. Among the swirling chaos of cosmic dust and gas, where most nebulae stretch into graceful, organic clouds, one structure stands out like a cosmic architect's blueprint: the Red Rectangle Nebula. Located about 2,300 light-years away in the constellation Monoceros, this glowing crimson enigma isn't just named for its color. It's a near-perfect geometric anomaly with concentric layers of gas and dust forming what looks like a three-dimensional X-shape or a ladder reaching into space. And the strangest part, we've never found anything else like it. At the heart of this mystery lies HD 44179, a binary star system where two aging stars orbit each other in a tight, fiery dance. The primary star is a post-red giant, shedding its outer layers in violent stellar winds, while its smaller companion stirs the ejected material into eerie precision. Here's where the magic, or rather the physics, happens. As the dying star pumps out gas and dust, the companion star's gravity sculpts that debris into twin conical outflows, like hourglass jets fired in opposite directions. But because we're viewing this system nearly edge-on, those cones overlap visually, creating the illusion of a rectangle. It's a cosmic trick of perspective, like staring at a spinning top from the side and seeing it as a flat line. Then there's that haunting red glow. Most nebulae shine in blues and greens, energized by young, hot stars. The red rectangle's crimson hue comes from a rare form of organic molecules called polycyclic aromatic hydrocarbons, or PAR, complex carbon-based compounds that flourish under ultraviolet light. These molecules are essentially soot, the same stuff found in car exhaust or candle flames, but here they're woven into the nebula's latticework by stellar winds. Some scientists speculate this could be how the building blocks of life hitch rides across the galaxy, seeding future planets with probiotic material. But geometry this precise doesn't come from chaos alone. The nebula's sharp edges suggest something else is at play, a hidden disk of dust around the binary stars, acting like a stencil that channels the outflowing material into those clean lines. Imagine blowing smoke rings through a keyhole. The disk's gravitational grip forces the ejector into orderly paths, creating the red rectangle's unmistakable structure. Over time, as the central stars continue to evolve, this cosmic artwork will dissipate, leaving behind only a white dwarf and a fading infrared echo. What makes the red rectangle so captivating isn't just its beauty, it's a laboratory for processes we rarely get to witness. From the physics of binary interactions to the chemistry of space-borne organics, every detail challenges our assumptions about how planetary nebulae form. It's proof that even in death, stars can create something extraordinary, a fleeting masterpiece painted in stardust and geometry, visible only for a cosmic blink before it's gone forever. At Saturn's North Pole, where most planets might host a simple swirling storm, something far stranger looms, a colossal, razor-sharp hexagon stretching wider than Earth itself. This isn't an artist's rendering or a trick of the light. It's a real, persistent structure, a six-sided vortex churning in Saturn's atmosphere for at least 4 decades, possibly much longer. Unlike the chaotic tempests of Jupiter or the fleeting storms of Earth, this geometric freak of nature defies every expectation, standing as one of the most baffling meteorological puzzles in the solar system. The hexagon was first spotted by NASA Voyager missions in the early 1980s, dismissed at first as a camera artifact. But when Cassini arrived decades later, there it was unchanged, a perfect honeycomb of wind circling the pole at over 300 miles per hour, its edges so precise they look laser-cut. What makes this even weirder, the hexagon isn't just a surface pattern. It's a towering structure plunging hundreds of miles deep into Saturn's atmosphere, like a cosmic drill bit frozen mid-spin. So how does a storm, a phenomenon we associate with chaos, hold such a rigid shape? The answer might lie in fluid dynamics, the same physics that governs everything from your morning coffee swirl to ocean currents. In labs, scientists have recreated rough hexagons by spinning liquids at different speeds, creating shear forces that segment the flow into geometric shapes. On Saturn, where the atmosphere is mostly hydrogen gas behaving like a supercharged fluid, the planet's rapid rotation, a day that lasts just 10.5 hours, might be sculpting the storm into this uncanny form. Some models suggest the hexagon acts like a standing wave, where faster and slower moving bands of atmosphere collide, locking the turbulence into a stable pattern. But there's a catch. Lab experiments produce fleeting polygons, not structures lasting generations. Saturn's hexagon has outlived multiple spacecraft missions, unfazed by the planet's seasonal changes or the churning chaos around it. This durability hints at something deeper. Maybe the hexagon is anchored by Saturn's internal dynamics, a manifestation of hidden jets or vortices deeper in its liquid metallic hydrogen core. Others propose it's a resonant phenomenon, like a musical note sustained by the planet's own rotation, with the hexagon as its visible vibration, the wildest theory. The hexagon could be a kind of cosmic Rossby wave, a planetary scale ripple usually seen in Earth's jet streams, but cranked up to alien extremes by Saturn's lack of solid continents to disrupt it. Imagine a ripple in a pond that never fades, trapped in perfect resonance by the pond's own shape. That might be the hexagon, a storm trapped in a loop feeding on its own energy. What's undeniable is this: Saturn's hexagon isn't just a curiosity, it's a challenge, a reminder that even in our own cosmic backyard, nature can craft phenomena so strange they force us to rethink the basics. Every time we study it, we're not just learning about Saturn, we're learning how fluid, how adaptable the laws of physics can be when stretched to planetary scales. And until we crack its code, that six-sided sentinel will keep spinning, silent and enigmatic, at the roof of Saturn's world. We think we know where most of the universe's matter is until we actually count it. Here's the problem: when astronomers tally up all the visible stars, galaxies, and gas clouds, they're left scratching their heads. Where's the other half of the normal matter, the protons, neutrons, and electrons that should be out there? This isn't dark matter we're talking about. It's the ordinary, everyday stuff that makes up planets, people, and everything we can see, and it's gone missing on a cosmic scale. This enigma, known as the missing baryon problem, has haunted astrophysics for decades. Baryons, the particles that form atoms, should account for roughly 5% of the universe's total mass energy budget, based on measurements of the cosmic microwave background. But when we add up all the luminous matter we can detect, we only find about half that amount. So where's the rest? The leading theory points to an invisible spiderweb stretched across the cosmos, a filigree of ultra-hot gas threads called the warm-hot intergalactic medium, or WIM. These faint tendrils, heated to millions of degrees but too diffused to glow brightly, might be hiding the universe's lost atoms in plain sight. Detecting this ghostly web isn't easy. The gas is so scorching that it emits X-rays, not visible light, and so thin that it's nearly transparent. Imagine trying to spot a single lit match in a foggy valley at night. That's the challenge astronomers face. But recent breakthroughs are cracking the case. By using distant quasars as cosmic flashlights, scientists have spotted the WIM's shadowy fingerprints. As quasar light passes through these filaments, certain wavelengths get absorbed, leaving telltale gaps in the spectrum like bullet holes in a crime scene photo. The European Space Agency's XMM Newton telescope has even caught faint X-ray glows from these structures, confirming they're real and packed with enough ionized oxygen and nitrogen to account for much of the missing matter. Here's where it gets stranger. These filaments aren't just passive cobwebs, they're dynamic, fizzing with energy. Supercomputer simulations show how the cosmic web formed. After the Big Bang, gravity pulled matter into vast sheets and strands, with galaxies forming at the intersections like dew on a spider's silk. The voids between, filled with WIM, a broth of particles so hot they're practically frictionless, streaming along magnetic field lines like commuters on unseen highways. Some of this gas might have been blasted out of galaxies by supernova shockwaves or supermassive black hole jets, littering intergalactic space with atoms like breadcrumbs from a cosmic feast. Yet mysteries remain. Even with these detections, we're still short a chunk of baryons. Some might lurk in even hotter, more elusive forms, or perhaps in regions too distant for current telescopes to probe. Future missions like NASA's upcoming Athena X-ray Observatory aim to map the WIM in higher resolution, hunting for the universe's last hiding places for ordinary matter. Because in the end, this isn't just about accounting for atoms, it's about understanding the skeleton of the cosmos itself. The cosmic web isn't just structure, it's the universe's circulatory system, channeling the raw materials for future stars, planets, and perhaps even life. And until we find every last baryon, we're missing half the story of everything. Galaxies should not spin as fast as they do, at least, not if the universe followed the straightforward rules of gravity we thought we understood. When astronomers first measured the rotation speeds of spiral galaxies like our Milky Way, they expected the outer stars to move slower than the inner ones, just like planets farther from the Sun orbit at more leisurely paces. But the cosmos had a different idea. Instead of gracefully slowing down, stars at the fringes of galaxies whip around at nearly the same speed as those closer in, as if some hidden hand were holding the galaxy together. This bizarre mismatch between prediction and reality is one of the strongest clues we have that the universe is packed with something we can't see, something we now call dark matter. The discovery traces back to Vera Rubin and Kent Ford in the 1970s, who meticulously tracked the motion of stars in the Andromeda galaxy. Their observations shattered expectations. According to Newton's laws, stars orbiting far from a galaxy's center should feel a weaker gravitational tug from the visible mass, mostly stars and gas, and thus move slower. Instead, Rubin found stars at the galaxy's edge hurtling just as fast as those near the core. The only plausible explanation, a vast, invisible halo of matter, far more than the galaxy's luminous parts, must be exerting extra gravitational pull, keeping those outer stars from flying off into space. Remove this unseen mass, and the galaxy would tear itself apart. But dark matter isn't the only contender in this cosmic whodunit. Some scientists argue that perhaps the laws of gravity themselves need rewriting. Enter modified Newtonian dynamics, and a radical tweak to Newton's equations that suggests gravity behaves differently at extremely low accelerations, like those found in galaxy outskirts. Proponents of MAN point out that it can explain galactic rotation curves without invoking invisible matter. It's an elegant idea, but it's far from perfect. While MAN works well for individual galaxies, it struggles to explain other phenomena like the way galaxy clusters move or the intricate patterns in the cosmic microwave background that dark matter handles with ease. Then there's the third possibility. Both theories could be wrong. Maybe the answer lies in something even stranger, like quantum gravity effects or undiscovered particle interactions. The debate rages because this isn't just about galaxies, it's about the bedrock of physics. If dark matter exists, it means the universe is mostly made of something we've never directly detected. If MAN is correct, it means our understanding of gravity, one of science's oldest and most trusted pillars, is incomplete. Either way, galaxies are spinning a mystery, and until we solve it, we're left staring at the stars, wondering what invisible forces are really at work. No matter where we look, the cosmic microwave background, the faint afterglow of the Big Bang, should be almost perfectly uniform, a tapestry of microwaves whispering the same temperature everywhere. But in the constellation Eridanus, there's a chilling anomaly, a cold spot so vast and so profound it defies easy explanation. This cosmic cold sore stretches over 1 billion light-years, a region where the CMB's temperature drops slightly but significantly, like a shadow cast by something we can't see. And the leading suspect, the Eridanus supervoid, an abyss of nothingness so enormous, it might just be the largest single structure ever discovered in the universe. Voids themselves aren't unusual. The cosmos is full of gaps where galaxies are sparse, like air bubbles in cosmic foam. but the Eridanus supervoid is different. It's not just empty, it's aggressively empty, a staggering spherical desert where galaxy clusters are suspiciously absent. If typical voids are potholes, this one's a sinkhole. And according to theory, such a vast emptiness could leave a thermal fingerprint on the CMB. Here's how: as light from the Big Bang travels through the supervoid, it loses energy climbing out of this gravitational valley, a process called the integrated Sachs-Wolf effect. The result, that light reaches us slightly colder than it should be, like a traveler exhausted after crossing a mountain pass, but not everyone's convinced. The cold spot is too cold, too large to easily fit our models of cosmic structure. Some simulations suggest a void this size should be exceptionally rare statistically. It shouldn't exist at all. That's led to wilder theories, like the idea that this cold spot is a bruise left by a collision with another universe. In certain multiverse models, neighboring bubble universes could theoretically bump into ours, leaving behind imprints in the CMB. It's a radical idea, but the math checks out if you're willing to entertain the existence of parallel realities brushing against our own. Skeptics counter that the cold spot might just be a trick of perspective, an accidental alignment of smaller voids that looks like a single giant structure from our vantage point. Others propose more exotic physics, like primordial cosmic textures, defects in space-time left over from the universe's birth, unraveling like a loose thread in the fabric of reality. Even the supervoid's own existence is debated. Some galaxy surveys find fewer galaxies there, but not the sheer emptiness required to explain the cold spot's depth. What makes this mystery so compelling isn't just the science, it's the stakes. If the Eridanus cold spot is proof of a multiverse, it would be the first tangible evidence that our universe is just one of many, a single page in an infinite cosmic library. If it's a statistical fluke, it means our standard model of cosmology might need serious revisions. Either way, this frigid anomaly is more than a curiosity. It's a crack in the foundation of everything we think we know. And until we solve it, that cold spot will keep staring back at us, silent and enigmatic, daring us to look deeper. Mars should be a dead world, geologically quiet, biologically barren, a frozen desert where the most exciting weather event is a whirling dust devil. Yet something on the red planet is belching methane into its thin atmosphere in unpredictable, tantalizing bursts, and we have no definitive idea what's causing it. This isn't just a scientific curiosity, it's a detective story with two possible culprits, each more intriguing than the last. Either Mars hides active geological processes we've never seen before, or whisper it, there might be life breathing beneath those rust-colored sands. NASA Curiosity rover has been smelling the Martian air since 2012, and its findings read like a cliffhanger. Methane concentrations spike sporadically, sometimes jumping tenfold in just hours before vanishing again. These pulses aren't random noise, they're localized, often detected inside Gale crater, as if something beneath the rover's wheels is exhaling on an erratic schedule. The numbers are small by Earth standards, parts per billion, but on Mars, where methane should break down within centuries under harsh ultraviolet light, even these whiffs imply an active, ongoing source. So where's it coming from? The geological explanation points to serpentinization, a chemical reaction between water, carbon dioxide, and certain minerals like olivine, which could produce methane deep underground. On Earth, this happens in hydrothermal vents where scorching water meets rock. If Mars has similar hidden hotspots, it would rewrite our understanding of the planet's inner workings, suggesting far more hydrothermal activity than we'd ever suspected. There's just one problem. No orbiter has spotted the heat signatures or mineral alterations we'd expect from such active sites. Then there's the elephant in the room: biology. On Earth, 95% of atmospheric methane comes from living organisms, from burping cows to subterranean microbes. If Martian microbes exist, perhaps deep underground, shielded from radiation, metabolizing hydrogen or carbon, they might produce methane as a byproduct. The gas's sporadic nature could even make sense. Perhaps it's being intermittently released when subsurface ice cracks, allowing trapped pockets to escape. But the plot thickens. Europe's Trace gas orbiter, designed specifically to sniff Martian methane from orbit, has mostly come up empty, its sensitive instruments detecting no more than trace amounts, far lower than Curiosity's ground-level spikes. This discrepancy has scientists at odds. Could Curiosity be kicking up methane-laden dust as it rolls? Is some unanticipated chemical reaction happening inside the rover itself? Or is the methane pooling near the surface in thin layers that orbiters can't see, like morning mist in a valley? What's undeniable is that every new measurement deepens the puzzle. Methane shouldn't behave this way. It should either be everywhere or nowhere, not playing hide and seek across seasons and locations. Future missions like NASA Mars Life Explorer aim to drill deeper and analyze carbon isotopes in the methane, which could hold the smoking gun. Biological methane tends to be lighter, enriched in carbon-12, while geological sources favor carbon-13. Even a single isotopic ratio could tilt the scales toward life or rock. Until then, the methane mystery stands as one of the most tantalizing threads in planetary science. It's a reminder that Mars, for all its barren appearance, might still hold secrets, whether in the stirrings of hidden volcanoes, the whispers of underground water, or the faint, stubborn signatures of something alive. Every whiff of gas is a clue, and we're just beginning to piece together what it's trying to tell us. After sunset or before sunrise, when the sky is darkest but not yet pitch black, a faint, ghostly glow sometimes rises from the horizon, a triangular shimmer stretching upward along the path where the sun and planets travel. This is the zodiacal light, a phenomenon long attributed to sunlight reflecting off cosmic dust scattered across our solar system's inner reaches. For centuries, astronomers assumed they understood its source: tiny particles left behind by comets and asteroid collisions, drifting in a vast disk around the sun. But recent discoveries have turned that tidy explanation on its head, revealing an eerie surplus of dust far more than known sources could possibly account for. The mystery lies in the numbers. When researchers calculated how much debris comets and asteroids should contribute over the solar system's lifespan, the math fell disastrously short. Estimates suggest we're seeing 10 times more dust than these sources could produce. It's like walking into a room expecting a handful of sand and instead finding a beach. Where is this excess coming from? One theory points to Jupiter's Trojan asteroid swarms of rocky bodies trapped in the planet's gravity wells. These ancient fossils from the solar system's birth might be eroding faster than we thought, shedding dust like dandelions in a cosmic wind. Yet even adding their potential contribution leaves a glaring gap in the ledger. Then there's the dust migration hypothesis. Some scientists propose that interstellar dust particles drifting in from outside our solar system could be getting caught in the sun's gravitational pull, funneled into the ecliptic plane like leaves gathering in a gutter. But this raises another puzzle. Why haven't we detected similar zodiacal light in other star systems? If dust migration were common, telescopes like Hubble or JWST should spot these glows around nearby stars. Instead, our solar system's zodiacal light seems oddly bright, almost as if something local is turbocharging it. The most startling possibility: a hidden population of undiscovered objects, perhaps millions of tiny, dark comets or icy bodies too faint for our telescopes, silently disintegrating as they loop through the inner solar system. Japan's Hayabusa 2 mission found evidence of such pebble pile asteroids, loose, fragile agglomerations of gravel that could crumble at the slightest solar heat, releasing torrents of dust. If these are more abundant than we realize, they might explain the surplus, but the plot thickens when you examine the dust itself. Observations from NASA Juno spacecraft revealed something bizarre during its journey to Jupiter. The dust particles hitting its detectors weren't just any debris, they were orbiting the sun in nearly perfect alignment, moving like synchronized swimmers rather than the chaotic cloud we'd expect. This suggests an unseen force, maybe electromagnetic effects or subtle gravitational resonances organizing the dust into eerily precise streams. What makes this more than an academic curiosity is what it reveals about our cosmic neighborhood. The zodiacal light isn't just a pretty glow, it's a forensic snapshot of the solar system's hidden activity. Every speck of dust holds clues about collisions, migrations, and processes we've yet to uncover. Future missions like Europe's Comet Interceptor might finally trace this dust back to its source. Until then, that ethereal light remains a silent question mark hanging in the twilight, reminding us that even in well-trodden corners of space, mysteries lurk just beyond the edge of our understanding. One of the most urgent puzzles in modern cosmology isn't hiding in some distant galaxy, it's baked into the very fabric of space itself. Scientists call it the Hubble tension, and at its heart lies a simple question with world-shaking implications. How fast is the universe expanding? The problem. We're getting two different answers, and the gap between them is widening into a chasm that could crack open our understanding of reality. For decades, astronomers relied on two primary methods to measure the universe's expansion rate, known as the Hubble constant. The first, the distance ladder approach, uses pulsating stars called Cepheids and cataclysmic supernovas as cosmic mile markers. By tracking their brightness and distances, we can calculate how quickly space is stretching. The second method looks back to the dawn of time, analyzing the cosmic microwave background, the afterglow of the Big Bang, to predict how fast the universe should be expanding today based on its infancy. Both techniques are meticulous, grounded in decades of research and independently verified, and yet they disagree by roughly 7.5%. That might sound small, but in cosmology, it's a screaming alarm bell. Imagine two clocks, both built by master watchmakers, both ticking perfectly, but one runs slightly faster than the other. At first, you might shrug it off, but over billions of years, that tiny discrepancy snowballs into a glaring paradox. That's the Hubble tension. The distance ladder method, championed by the Hubble Space Telescope, suggests an expansion rate of about 73 kilometers per second per megaparsec. Meanwhile, the cosmic microwave background, mapped in exquisite detail by the Planck satellite, points to a slower 67. The difference adds up over 1 million light-years. Those missing kilometers per second imply a universe expanding faster than our models allow. What makes this more than a technical hiccup is what it implies about the laws of physics. If both methods are correct, and repeated checks suggest they are, then something fundamental is missing from our equations. The standard model of cosmology, our playbook for the universe, might need rewriting. One tantalizing possibility: dark energy isn't constant. This mysterious force driving cosmic acceleration could be evolving, growing stronger over time. Alternatively, there might be a fourth, undiscovered type of neutrino, a sterile neutrino, adding extra energy to the early universe and throwing off our predictions. Then there's the nuclear option. What if gravity itself behaves differently on cosmic scales? Einstein's theory of general relativity has passed every test we've thrown at it, but the Hubble tension could be the first crack in its armor. Some theorists propose modifications to gravity's equations, introducing subtle tweaks that only kick in across vast distances. Others wonder if we're seeing echoes of a baby universe that existed before the Big Bang, leaving fingerprints on our expansion rate. The stakes couldn't be higher. If the Hubble tension holds, it means the universe is playing by rules we haven't discovered yet. Every new measurement, from next-generation telescopes like the James Webb Space Telescope to groundbreaking surveys of supernovas, tightens the screws on this mystery. Some scientists cling to hope that hidden errors lurk in the data, but as methods improve, the discrepancy only grows starker. What's thrilling isn't just the potential for new physics, it's the humility it forces upon us. For all our telescopes and supercomputers, the cosmos still guards its secrets fiercely. The Hubble tension isn't just a numbers game, it's a cosmic dare challenging us to look deeper, think harder, and admit that even our best theories might only be scratching the surface. And until we solve it, every answer we find only leads to bigger questions. Far beyond Neptune, in the icy fringes of our solar system, something isn't playing by the rules. The Kuiper Belt, a donut-shaped region teeming with frozen leftovers from the solar system's birth, should be a place of orderly chaos, with objects scattered randomly in all directions. But a handful of these distant bodies are doing something peculiar. Their orbits are tilted, clustered, and aligned in ways that defy simple chance. It's as if an unseen hand has reached into the cosmic deep freeze and given them a nudge, bending their paths into a pattern that shouldn't exist without some hidden influence. This odd orbital dance has sparked one of the most tantalizing theories in modern astronomy, the hunt for Planet 9. The clues first emerged when astronomers noticed that several extreme Kuiper Belt objects, icy worlds like Sedna and 2012 VP-113, shared bizarre orbital traits. Instead of circling the Sun in the flat plane where planets orbit, these objects swing far above and below it, their paths stretched into elongated ellipses. Even stranger, their closest approaches to the Sun all huddle in roughly the same patch of sky, as if they'd been herded there by some gravitational shepherd. The odds of this happening randomly, less than 1 in 10,000. That's where Planet 9 enters the picture. Proposed in 2016 by Caltech astronomers Konstantin Batygin and Mike Brown, the idea is simple: a massive, undiscovered planet, perhaps 5 to 10 times Earth's mass, could be lurking hundreds of times farther from the Sun than we are. Its gravity would act like a cosmic wrecking ball, perturbing the orbits of these distant objects over millions of years, sculpting them into the strange alignment we see today. Simulations show it's possible. Toss a hypothetical Planet 9 into the outer solar system, and over time it does produce the observed clustering. The math fits, but only if the planet is out there. Yet not everyone's convinced. Skeptics argue that observational bias could be at play. Maybe we've only spotted these odd orbits because telescopes are looking in certain directions, missing others that would break the pattern. Others propose that the collective gravity of many smaller Kuiper Belt objects might explain the anomalies, like a crowd subtly shifting the path of a rolling marble. There's even a radical idea that dark matter, if it's unevenly distributed in our solar system, could be tugging on these icy worlds. But Planet 9's allure isn't just scientific, it's poetic. The idea that our solar system might still hide a world large enough to be called a planet feels like a throwback to the days of astronomical discovery, when each new telescope sweep could rewrite the map of the heavens. And the hunt is on. Telescopes like Subaru in Hawaii are scanning the skies for faint glimmers of movement, while mathematical models narrow the search zone. Every unexplained wiggle in a distant object's orbit is another breadcrumb, another hint that something big might be lurking in the dark. What makes this mystery so compelling isn't just the potential prize, it's what it says about our cosmic blindness. Even in our own celestial backyard, there are forces at work we don't fully grasp. Whether it's a hidden planet, a swarm of unseen objects, or something even stranger, the Kuiper Belt's oddballs are a reminder. The solar system isn't done surprising us yet. Until we find or rule out Planet 9, those tilted, clustered orbits will keep whispering the same tantalizing question: what's out there? At the heart of our galaxy, where stars crowd together in a chaotic dance around a supermassive black hole, there's a glow that shouldn't exist, a persistent hum of gamma rays radiating from the Milky Way's core with no obvious source. This mysterious emission, known as the galactic center excess, has split astronomers into warring camps, each armed with competing theories about what could possibly be pumping out such intense energy. The leading suspects, either an invisible swarm of dark matter particles annihilating each other in the void, or an uncountable army of ultra-dense stellar corpses spinning silently in the dark. The case for dark matter is tantalizing. Simulations have long predicted that our galaxy's core should be packed with this elusive substance, drawn inward by Sagittarius A's monstrous gravity. If certain theoretical particles like WIMP, weakly interacting massive particles, exist, they might occasionally collide, annihilating in bursts of energy that could explain the gamma-ray excess. It's a beautiful idea, neatly solving two mysteries at once, the nature of dark matter and the unexplained glow. But there's a catch. The signal's distribution isn't perfectly smooth as dark matter models predict. Instead, it's slightly lumpy, like a spotlight shining through a torn curtain. That texture has led skeptics to argue the glow might come from something far more mundane: pulsars, the lighthouses of the cosmos. These spinning neutron stars, left behind after supernova explosions, emit beams of radiation that sweep across space like cosmic strobe lights. Thousands of them could be lurking unseen in the galactic center, too faint to spot individually but collectively producing the gamma-ray haze we observe. Recent studies have even found faint point sources hidden in the excess, hinting at hidden pulsars. But here's the twist: the number required strains plausibility. To match the signal, there'd need to be tens of thousands of these stellar remnants crammed into the inner galaxy, far more than our models of star formation predict. The debate rages because the stakes are cosmic. If it's dark matter, it would be the first tangible clue to its identity after decades of fruitless searches. If it's pulsars, it means the galactic center is even more extreme than we imagined, a graveyard of dead stars defying expectations. Some researchers suggest a third path, maybe it's both. A mix of pulsars and dark matter, their signals overlapping in a way we can't yet untangle. Others propose wilder ideas, like primordial black holes from the Big Bang or even exotic particle collisions near Sagittarius A. What's undeniable is this: the galactic center excess isn't just a scientific disagreement, it's a frontier. Every new observation, from gamma-ray telescopes like Fermi to radio surveys hunting hidden pulsars, chips away at the mystery. Until we know for sure, that eerie glow will keep burning at the heart of the Milky Way, a silent challenge to our understanding of the universe's darkest secrets. The universe isn't just dotted with galaxies, it's threaded by them, woven into vast filaments and sheets that stretch across billions of light years like a cosmic spiderweb. But between these glittering strands lie gaping chasms of nothingness, regions so eerily empty they defy logic. These are the cosmic voids, and the largest among them aren't just gaps, they're staggering, near total vacuums where galaxies are almost non-existent. One of the most infamous, the Boötes Void, spans 330 million light-years and contains less than 60 galaxies. To put that in perspective, a patch of space that size should host thousands. It's not just an absence, it's a cosmic crime scene, as if someone scooped out the universe's contents and left behind a hollow sphere of darkness. How does something this empty even form? The leading theory points to the aftermath of the Big Bang. In those first chaotic moments, quantum fluctuations created ripples in density, some regions slightly denser, others slightly sparser. Over billions of years, gravity amplified these differences, pulling matter into filaments and leaving behind bubbles of near-nothingness. But the Boötes Void and others like it push this idea to its limits. Simulations suggest voids should be smaller, or at least peppered with more galaxies. Their sheer scale hints at forces we don't fully understand, perhaps relics from the universe's birth, like defects in spacetime itself, or echoes of an inflationary phase that stretched some regions far more than others. Then there's the unsettling possibility that these voids aren't entirely empty. Dark energy, the mysterious force accelerating the universe's expansion, might dominate these regions, creating repulsive gravity that actively pushes matter away. Imagine blowing up a balloon with a few dots on it. The dots move apart as the balloon expands, but in voids, it's as if the balloon's fabric itself is stretching faster, leaving the dots isolated. Some theorists even speculate that voids could be home to exotic particles or fields we've yet to detect, lurking in the darkness like invisible tenants. What makes these voids more than just cosmic curiosities is what they reveal about the universe's structure. They're not passive holes, they're dynamic, growing over time as their gravitational pull weakens and matter flees toward denser filaments. This creates a feedback loop. The emptier a void gets, the more it repels and the faster it grows. In a sense, voids are the architects of the cosmic web, their expansion shaping the paths along which galaxies flow. But the real mystery isn't just their size, it's their edges. Some voids appear unnaturally sharp, as if carved by an unseen blade. Others show faint, filamentary bridges of matter threading through them like spider silk across a cavern. These structures challenge our models of cosmic evolution, suggesting that voids aren't random but organized in ways we're only beginning to grasp. Future telescopes like the Vera Rubin Observatory aim to map these voids in unprecedented detail, probing their depths for clues. The most haunting thought, voids might be windows into the universe's fate. As dark energy accelerates expansion, the entire cosmos could one day resemble a void, galaxies isolated, stars unreachable, space itself stretching into infinite silence. For now, these great nothings stand as both puzzle and prophecy, reminding us that in the tapestry of the universe, emptiness can be just as telling as light. One day, billions, perhaps trillions of years from now, the universe will breathe its last, but how that final moment unfolds depends entirely on a cosmic tug of war we're only beginning to understand. Will space collapse back into a singularity in a fiery big crunch? Will it fade into an eternal, frozen darkness? Or could this be just one act in an endless cycle of cosmic rebirth? The answer hinges on dark energy, that enigmatic force accelerating the expansion of the cosmos, and whether its grip will tighten, weaken, or someday snap. For much of the 20th century, astronomers assumed gravity would eventually win. In this big crunch scenario, the universe's expansion would slow, halt, then reverse as matter pulled everything back together in a cataclysmic collapse. Galaxies would merge, temperatures would soar, and ultimately all existence would compact into a singularity, a mirror image of the Big Bang. It's a dramatic vision, one that implies cosmic cycles: bang, expansion, crunch, and repeat. But then came the bombshell discovery in the late 1990s. The universe isn't slowing down at all. It's accelerating, propelled by dark energy's repulsive force. Unless that force changes, the big crunch is off the table. Instead, the leading contender now is heat death, or the big freeze. Here, dark energy keeps stretching space indefinitely, diluting matter and energy until the cosmos becomes a vast, lifeless graveyard. Stars burn out, black holes evaporate via Hawking radiation, and eventually even atomic motion grinds to a halt. Temperatures approach absolute zero, and time itself loses meaning. It's a chilling prospect, but not the only possibility. Some theorists argue dark energy might evolve, growing stronger to trigger a big rip. In this nightmare scenario, the accelerating expansion would overpower gravity, electromagnetism, even nuclear forces, first shredding galaxies, then stars, planets, and finally atoms themselves in a violent crescendo of cosmic disintegration. Yet there's a third, more poetic option: cyclical universes. String theory and certain cosmological models suggest our universe might be one in an infinite series, each ending in a big crunch that births the next big bang. Others propose a bounce, where the universe collapses only to rebound, like a spring compressed to its limit. These ideas often hinge on dark energy weakening over time, allowing gravity to regain dominance. Intriguingly, some observations of distant supernovas hint that dark energy's strength might not be constant, but the evidence is far from conclusive. The wild card in all this, quantum physics. Vacuum fluctuations could spawn new universes in a process called eternal inflation, meaning even as our universe dies, others might bloom elsewhere in the multiverse. Or perhaps an advanced civilization could engineer a cosmic reset, harnessing energies beyond our imagination to stave off oblivion. What's certain is this: the universe's fate isn't just a philosophical thought experiment. It's written in the subtle behavior of dark energy, the curvature of space-time, and the fundamental laws we're still unraveling. Every measurement of distant supernovas, every study of the cosmic microwave background, brings us closer to forecasting the ultimate destiny of everything. And until we know for sure, the cosmos keeps expanding, carrying us toward an ending we can predict but not yet prove. From the haunting whispers of the Wow signal to the cosmic ghost town of the Boötes Void, we've journeyed through 25 of the universe's most jaw-dropping enigmas, phenomena that defy logic, challenge physics, and remind us just how little we truly know. Think about it: dark matter's invisible grip, dark energy's relentless push, galaxies spinning faster than they should, and stars flickering like cosmic light switches with no explanation. We've stared into the abyss of the Great Attractor, wrestled with the black hole information paradox, and wondered if Oumuamua was a visitor from another star, or something far stranger. These aren't just puzzles, they're doorways. Every unexplained signal, every anomalous orbit, every void in the cosmic web is a crack in the facade of our understanding, hinting at forces and laws we haven't even dreamed of yet. The universe isn't just hiding its secrets, it's daring us to look closer, to question harder, to admit that for all our telescopes and supercomputers, we're still just scratching the surface. So what's your favorite cosmic mystery? Is it the eerie precision of Saturn's hexagon, or the chilling silence of the Fermi Paradox, the way Tabby Star dims and brightens like a cosmic co-conspirator, or the spine-tingling possibility that Planet 9 might be lurking in the shadows? Drop your thoughts in the comments. Let's geek out over the universe's greatest unsolved riddles together. And if you're hungry for more mind-bending explorations, hit that subscribe button. Because here's the thing, the cosmos isn't done surprising us. Every discovery peels back another layer, revealing just how wild, how weird, and how wondrous reality really is. So keep looking up, keep asking questions, and remember, somewhere out there, in the black between the stars, the next great mystery